We'll do some simple experiments, but the simple experiments are the most interesting ones sometimes, because they show people's ignorance sometimes, or misconceptions. Okay, so here is the can. I'm going to do something very, very simple. This can is rolling on the tabletop without slipping. Okay? Is the can rotating, yes or no? Yes. Now, if you have an object rotating, there is an axis of rotation. What is the axis of rotation? The center of the can, right? Everybody agrees? Who disagrees that it's the center of the can? Like I said, misconceptions. You've played with rolling things and wheels and bicycles and tricycles and toy trains and toy cars and road rage Barbie or whatever. And yet you have not a clear idea about rolling motion. The wheel is the greatest invention of mankind, so we have to understand it when we take a physics course. Okay. So I'm going to convince you that the center of the can or anything rolling is not the axis of rotation. But first let's understand what axis of rotation is. It's that point that is fixed while the rest of the body moves around it. Okay? We agree? Okay. Alright, so I'm going to have a series of experiments here. And this is a very simple experiment. This is as you can see, a meter stick that is pivoted. It can move around. And I'm going to pull on it like this. I'm applying a force in that direction, right? And in what direction is the meter stick rotating? It's rotating, as you see, counterclockwise, right? Counterclockwise. So let me raise this some more and pull on it. Counterclockwise? Yeah, counterclockwise. Let me go up here. Counterclockwise? Yeah, counterclockwise. Let me go up here. Counterclockwise? Yeah, counterclockwise. Let me go all the way up here. Doesn't rotate, does it? No, of course not. Because I'm pulling right at the pivot. And the torque is zero because there's no lever arm. Okay? Alright. So what I'm going to do then is move this above the pivot and pull at the pivot. Is it rotating? Yeah. Let me go a little bit higher. Which way is it rotating now? Clockwise. The rotation reverse direction, the torque reverse direction. And if I move farther and farther up, you can easily be convinced I'm not that tall to get it stuck. It's still clockwise. Right? So what have we learned from this? That if I pull in that direction, as long as I am below the pivot point, it's counterclockwise. Above the pivot point is clockwise. Okay, let's write this down. Below pivot, what did we say? Counterclockwise, CCW. Above pivot, what did we say? Clockwise. Okay. Got it? Good. Let's go here to this guy over here. It's like a yo-yo. And what I'm going to do is do the same thing. Okay. I'm pulling in this direction. Below the pivot point, counterclockwise. So I'm pulling below the pivot point. What do you think the pivot point is? The axis? Okay. Let's move farther up. Am I still below the pivot point? Yeah? Yeah? Anybody disagrees? Okay. Let's move up here. It's not moving, I'm pulling. Let's go a little bit higher than this point. The pivot point is right here. which is the point of contact with the tabletop. That's where the pivot point is. And instantaneously, this rolling wheel rotates about that pivot point. This point right here is at rest. This point has some angular velocity with respect to the point of contact. And this point also, everybody here on this rigid body has the same angular velocity, but the linear velocity is different. How so? Well, let's draw a picture of this thing. And here's a wheel. Okay. There's a point of contact. If it rolls without slipping, let's say I have a point B here and a point Q on the surface. These 2 points, one is on the wheel, right on the surface, one is on the table. These are instantaneously at rest. In what sense? In the sense that this is rolling without slipping. In other words, the 2 points, the 2 surfaces don't drop past each other. That's what I mean by instantaneously at rest. Okay. So now, instantaneously, the whole body is rotating about this point right here. And if the center of mass is moving with velocity v cm, and the angular speed is omega, then you know what the relation is. If the radius of this object is r, then omega times r is the linear speed of the center of mass. Okay? Everybody got it? Okay, pop quiz now. Let's see how well you got it. Yeah. We're done. Experiment number 3. Then we'll do the can. We'll bring out the big artillery. Big artillery. I think his name is on the... I want to pull from the top first. Yeah. Okay? Yeah, let me do it. So now, let's wrap it around some more. Again, I'll pull in the same direction. Okay? So, in what direction, if I pull this way, if I pull that way, in what direction is yo-yo ma going to rotate? Clockwise. In what direction is he going to move? The same direction as the force or opposite direction as the force? Can't hear you. Same direction. Let's see if that's the way it happens. Yeah, that's the way it happens. Okay? Now I'm going to turn him upside down. I pull in the same direction. What direction is yo-yo ma going to go? Same direction as the force or opposite? Opposite. Opposite? Anybody same direction? You learned nothing. You learned nothing. As I said, the point of contact is the pivot. In both cases, where I'm pulling this way or the other way, I am above the pivot. Above the pivot, clockwise. Got it? Got it. Good, thank you. All right. There are many misconceptions about rolling wheels. Now, with this picture, we have a prediction. And the prediction is that if, you know, the general expression for the relation between linear speed and angular speed is v equals omega r. Okay? Which means that if I look at this point here, then since the distance from the axis of rotation is twice as big, then it should be moving twice as fast. Do you believe that? Yes. Yes, you gotta believe that. Let's see if that is the case. Or are you too scared about your preconceptions now? It's in the equations. Okay, so what I'm going to do is I'm going to start this and I'm going to roll it with a meter stick on top. Okay, so that the the can and the meter stick roll without slipping on each other, and so does the tabletop. And what I'm going to do is mark the starting point. I'm going to use this eraser to mark the starting point. Okay? And you see that the center of the can and the meter stick are at the same point here. And as I move along, okay, here now is the center of the can. Here is the end of the meter stick. The end of the meter stick moves from here to there. The middle of the center of the can moves from there to there. Half the distance in the same amount of time. It has to be moving at half the speed, therefore. And in general, we can generalize this picture and draw velocity vectors so that over here, the velocity vector will be twice as long. So this will be 2 VCM, where VCM is given by this relation here. And in general, if I have, say, a point over here, then in order to draw the velocity vector, I need to draw the radius r. Remember now, in this equation, r is the distance between the axis of rotation and the point of interest. So this is r now. This point is going around in a circle centered at point P. And if it is going around in a circle, it has to make a right angle. And the velocity vector then will be drawn like this. And the speed then, v at this point, is equal to what? Well, what is r? Since this is the diagonal of the square, it's r times square root of e. And that's the direction. And so on for any other point. You can generate arrows showing the direction of the velocity at any point. Okay? Any questions? Yes?
I'm sorry, I still don't really understand how you got the velocity.
Which one?
The one at the bottom.
This one?
Yeah.
Okay. Are you convinced that all the points on this wheel now, if the wheel is moving forward in that direction, all the points on this wheel are instantaneously moving in a circle?
Yeah.
Okay. If it's a circle, here now, the center of the circle is this point right here, the point of contact. Okay? So, for this particular point of interest, let's call that point S. Okay? For point S, the radius of the circle is this diagonal here. Okay? And if it's going around in a circle, anything that goes around in a circle, if you connect a line from it to the center of the circle, that makes a right angle with a direction of motion. Okay? So there is a right angle. That's how I got it. Is that clear now?
Yeah.